Hello everyone. Well, we've moved on to the next module, and in this next module, I'm going to show you how to build your first predictive model. Maybe not your first predictive model, but for some of you it might be your first predictive model. And we're going to use a tool that is fairly simple, one called linear regression. Now, if you've done statistics in the past, you might be familiar with linear regression. And as we build a model, we're going to use Microsoft Excel to actually build our model. Linear regression is going to give us a couple of key values that we can use to take an independent variable and for each instance or each record in our data set, use that independent variable to predict the outcome value or predicted value for a dependent variable. So hopefully this will make sense to you as we get through this. First of all, I want to step back for a second and talk about the branches of analytics. We haven't talked too much about this, if at all, but there are different branches of analytics. There's descriptive analytics, and descriptive analytics is what we use to determine what's really going on with the data that we have. If we're working in an organization, we may be accumulating data on customer records or student records, and we are sitting down and looking at what that data is telling us. Discovery is similar to that. Discovery is beyond what the data is showing us kind of right in our face, what else can we discern or figure out from the data that we currently have today? And so that becomes very useful in using the existing data to find new insights. Predictive data is what can our data tell us about what's likely to happen in the future? And there's no magic going on here. Most of what we learn about what's likely to happen in the future is based on what happened in the past. And we're just carrying forward the patterns and the relationships between our data points from the past to the future using some method of prediction or forecasting. Prescriptive is where we learn what we should be doing with our data. Now that we know kind of what our data is, what we can discover about it, what it can tell us about the future, what should we do? And that's where prescriptive analytics comes in. So far, many of the tools that we've talked about have really focused a whole lot about descriptive and discovery analytics. Well, what we're going to do now is we're going to take a look at some predictive models, in particular, a linear regression model. So we're going to build a predictive model. Okay, what does that mean? That means we are going to use old data to predict the future. Now, building a predictive model works best if we have a lot of old data. It doesn't work too good if we don't have much old data. In our particular example, we don't have a lot of old data, but we're using small sets so that we can actually illustrate what it is we're looking at. It works even better if the fields that we want to use are independent and dependent variables, if there's already a relationship between those two. Now, if those two have nothing in common, it's going to be very difficult for us to use an independent variable to predict a dependent variable, especially if they have nothing in common. So we're going to assume or hope that they have something in common. Now, generally, we will logically know what that is. And we also get statistics when we run linear regression that tells us how well our model fits. So we'll know if we've got a good model or not. We have independent variables. Those are the variables that can be the predictors. Okay? And then we have dependent variables. Those are the variables that can be predicted based on the behavior of the predictors or the independent variables. This will all become clearer as we work through examples. A good example here, simple example here, the amount that you study, your independent variable, you have total control over it, you determine what it is, so it's an independent variable. The amount that you study will determine your exam score. Your exam score is dependent, it's a dependent variable, it's dependent on the amount that you study, your independent variable. What we could do here is we could build, if we had enough data, we could build a linear regression model that would show us the relationship between the amount that you studied and your exam score. And if we had enough data, and if those two things were related closely enough, we could, without having exam scores in future data sets, we could just take the amount of time that you study and predict what your exam score is going to be. That's what we're going to talk about today. So independent variables predicts the dependent variable. And here's how we build our model. First of all, we get an old data set. And the old data set has both the independent values and the dependent values. So that would be if we had, for example, our time of study and our exam scores, we would get a collection of records that had both of those values there. And we use both of those values to determine what the relationship is between the independent variables and the dependent variables. So we build that relationship, we examine that relationship and see, when one goes up, how much does the other one go up? When one goes down, how much does the other one go down? So by having those values, we were able to calculate two key values. And in linear regression, the two probably most important values are going to be something called the slope and the intercept. The slope and the intercept define the relationship between our independent variables and our dependent variable. So there will be a slope and an intercept that helps determine how the time of study and the exam score are related to each other. Then we use that on new data. We build a model actually using the slope and intercept, and we use that model on new data. So imagine now we're weeks into the future and we've got a new file, and all we have is the list of how much each student studied, how much time each student studied, but we don't know what their exam score is yet. So what we can do is we can use our model that we've created, we can feed in the time that each student studied and spit out a predicted exam score based on that value. Here's a sales example, and this is a kind of a key example because we're going to actually do this. We're going to look through an example file. I'm going to show you my own, and then I'm going to give you one, and your assignment will be to do the exact same thing on a different file. So imagine we're a retailer, and each year we track the total sales per customer, how much they buy from January 1st to November 30th. Then we ask, is that number a good predictor for how much they're likely to spend at Christmas time? So if they spend a lot from January 30th to November, or from January 1st to November 30th, are they likely to spend a lot, a little, or is there really no prediction there? Is there really no relationship between those two things? If it is a good predictor, then that helps us because now we can say, okay, these guys who spend a whole lot in the first 11 months of the year, come Christmas time, we're going to blast them with advertising, or we're going to give them special deals, or we're going to do whatever we would do as a retailer. But those that have really a small amount and are unlikely to spend a lot at Christmas time, well, we're going to take a different approach towards them. So there are mathematical formulas that will help us with all this. And again, like I said, we're going to use linear regression to determine this. Here's a side note on some terminology, and I just want to define this terminology because it's something you probably hear, and for the first time, it's something you're going to actually encounter. First of all, supervised versus unsupervised learning. Supervised learning is where we build a model, and we build a model on old data. That's the simplest way to put it. We use old data to build a model, and that's what we're doing today in this video, is we're going to use old data to build a model using a supervised learning algorithm, and the supervised learning algorithm is going to be our linear regression model. So unsupervised learning does not use old data, it uses the data at hand. Not terribly relevant for this, except for the fact that, like I said, our supervised learning, our supervised model that we're going to use training data, and I'm going to give you a training data set, and it's the training data that you're going to use to establish your predictive model. Now, if we were doing a really careful analysis of this, we would have multiple types of data. We could have training data, of course, to build the initial model, but then we would also have a validation set that looked very much like the training set. When we get a result for our training data that tells us how good our model is, we might run it against the validation set and see if we can just get sort of a second look. It's a different data set. We want to make sure that it is as good as the training data has suggested that it is. We might also use test data, and test data is kind of a third check. It's not data that came from the same source as the training or validation data. It's just a completely separate data set, and we're going to check it again and see how well the model works. We use test data sometimes because if our training data and our validation data are pulled from the same data source, we may build a model that is too carefully fit to those two training sets, and that means that our model isn't as accurate. So by pulling in a test data set from a completely separate source, we are going to find ourselves being able to test it independently. So again, that's a side note on terminology. Just suffice it to say that for our linear regression model that we're building today, we are going to use a training data set. We will not validate the model. Okay, so what about the training data? What are we going to learn from the training data? As I've indicated before, it's about what has happened in the past. So what has been the relationship between the variables in past data? And how much data is this based on? And by understanding the relationship between one variable and another in past data sets, we can predict how similar data sets will behave in the future. So can we put a model that takes input variables, or can we build a model that takes input variables and outputs accurate predictions? And again, our example is going to be sales for the year and Christmas sales. Okay, linear regression as a prediction method. This is one of many prediction methods, and it's a really popular one, but it has its limitations, and it has its limitations in the fact that it is linear, so it doesn't handle nonlinear data very well, and it only predicts one period into the future, because we have to look one period to the past to determine what one period in the future is going to be. The other thing is that a linear regression model is built on past data. When you collect more data and more data and more data, it may be worthwhile to run that additional data through and enhance your model, make your model actually more accurate. So, but a bit about it. So what we're asking is, what is the linear relationship between variable A and variable B? Okay, otherwise known as the input variable X and the output variable Y. And the X and the Y are key here. And it's going to be key here when we go into Excel. Your X is your predictor or your input variable, and it can be multiple variables, just to know, but we're only going to work with one today. Your output variable is your Y. It's your Y variable or your predicted value. Input X is the independent variable, output Y is the dependent. And it changes, the dependent variable changes when the input variable changes. But to what degree? The value or the model that we're going to use, the equation that we're going to use, is a standard linear regression equation. And it says that the value of Y is equal to something called the slope plus the intercept times the value of X. When we run the linear regression process in Excel, Excel will give us the value for slope and it will give us the value for intercept. Okay? Then what we need to do is we need to determine all of the values of X. We just plug them into this equation. And for each value of X, we're going to get a value for Y. And that's going to be able to be the way that we use X, the input variable, to predict the output variable. But what are the slope and intercept? Well, the slope is simple, sort of. For every increase, every single unit increase in the input variable X, the slope is how much that value will increase on Y. And this is much better looked at visually, so we'll go through it. And the intercept is, or I'm sorry, I got this wrong actually. Slope plus intercept. Yeah, this is wrong. Ignore this linear regression equation because it's wrong. I have it correct in another place, and I'm just going to move on to that. Okay, so we're using X to predict Y. Here we have a scatter plot, and this is our X-axis. And in this particular case, we were using petal length and sepal length, and these are parts of flowers. And we're saying that if one is long, then the other one is long. If one is short, then the other one is short. Seems pretty intuitive, right? So we're looking visually at our data set. And we need to know some stuff about the data set. First of all, we do see a relationship because it does seem like it goes on a diagonal line. So that seems to suggest that there's a relationship. X is in some way related to Y. Is the relationship strong enough? Do we have enough data? And what is the regression line? Well, the regression line is something that we use to determine the best possible position where the line that we're drawing is as close as possible to all of the data points. Okay? Imagine that we drew a diagonal line right through the middle of these data points. Where exactly should that diagonal line be placed to be as close as possible to every single data point? Now, if we put the diagonal line over here, we're going to be close to some of these data points, but we're going to be really far away from a lot of the data points. If we put the diagonal line here, same kind of thing. We'll be close to some of them, but really far away from other ones. So what we're going to do probably is draw right down the middle. And even though there's going to be some that are far away, most of them are going to be fairly close. And even the ones that are far away, we've minimized the overall total amount of distance between all of the data points and our line. Okay? And that becomes important because our line really is what determines both the slope. The slope of the line is where the line is actually positioned. And the intercept is the place where the line crosses the vertical axis. So if our line started here, and this would be, looks like it's 4, and cut through these data points up here, we would have an intercept of 4, and we would have a slope that is equivalent to the value that determines how steep that line should be. Okay? So those are the two values that we're really looking at. We're really looking at the slope and the intercept. And there's a mathematical method of calculating the intercept value, or the slope value. The slope value is rise over run. And what that basically means is that for every unit that you move from the left to the right, there's going to be an amount that you go over, and that's 1. And then there's going to be an amount that you go up, and that's going to be your rise. So your run is 1, your rise is some value. And the rise over run is going to be what determines the slope of that line. Okay, so again, to recap, slope and intercept. Intercept is where we hit the y-axis, and slope is what determines the steepness of your line. Here's an example of the line actually drawn. So turns out we were pretty close on our intercept. Our intercept is actually a little bit less than 5, so maybe 4 1/3 is where we're intercepting with the vertical axis. And then the slope is rise over run. And in this case, the intercept is 4.31, pretty close there, and our slope is 0.41. For every unit we move across the x-axis, we go up 0.41. So you can see that determines the steepness of the line. That is giving us the best fitting line that comes the closest to all data points, as close as possible to the whole collection of data points. That's your slope and intercept. Another example that was commonly cited in statistics textbooks is cricket chirps and temperature. A guy by the name of Dolbear found that when the temperature goes up, the number of chirps in a particular minute goes up as well, cricket chirps in a particular minute. Is it a fixed and predictable amount? Well, that's pretty close. He was able to use that and determine that there is a relationship between those two variables, and you can actually use the number of cricket chirps to predict the temperature. So cricket chirps could suddenly become your thermometer. But it has errors, and all models do have errors. When we are making predictions, we are never going to be 100% accurate. Let's talk about error, or what we also know as residuals. So we've already talked about slope and intercept. And we've talked about our equation where y is equal to the slope times x plus the intercept. Okay? One thing that's missing off of that equation is the error, and that's the difference between what we actually saw in our training data and what we predicted we would see in our training data. And this is really important because the residual, or the error, helps us determine the quality of our predictive model. So we'll use this one as an example. We have an input of x cricket chirps. We calculate the slope and intercept. That leads us to a predicted y value for each x. But reality, the actual measurement, which we might refer to as z, might be different in the training data set. So z is the actual measurement for each x, and E is the difference between Y and Z, or the error, the residual, what's left over. Okay. We come down here, we can see our actual Y is equal to our X times our slope plus our intercept plus our error. And that becomes the difference between the predicted Y and the actual Y. With the predicted Y, we're just looking at Y equals X times slope plus intercept. And we're not worried about error because it's our prediction. But in our actual Y, we're worried about the error, and we want to look at the error. Now, if the errors are really small, that's great. That means we're predicting really well and we're really close. If the errors are really large, that's not so good. And if you've got a mix of large errors and small errors, that also can be not so good. But we have a way of being able to determine what that error looks like and how much error there is and whether or not our model is actually any good. And I'll go through that in a bit. The best models have the lowest errors. The regression line is determined using the lowest cumulative error. So when you saw that line going through the scatter plot, that was actually placed there because it generated the lowest error across all of the data points for every data point. The quality of prediction is dependent on the size of the errors. That's the cumulative size of the errors. And error is a factor of the quality and size of the initial data set. So error could be determined by, or it could be really dramatically impacted by the number of records that we have and how good the relationship is between the two variables that we're looking at. In short, error is how far off we are for each of our predictions, and cumulative, when you add it all up across the entire data set, we want it to be as small as possible. So look at this visually. We have, this one actually is a little bit off, but if you look at this, this is our line, our linear regression line, and you can see that there are a couple of data points that are right on the line. They have very small errors. Their predicted value and their the predicted value, of course, is going to be on this line. That's the line that we would use to actually predict at what X do we get a Y. In many cases, for many of these data points, it's very close. But in some cases, like up here and down here, we're pretty far off. And again, it's going to be the scatter of the data points around the regression line that determines how good of a quality job our model is going to do. And then, of course, we can calculate a cumulative error. We measure if we have 100 data points in our set, we can measure the error for all 100 data points, take the absolute value, and either take a mean or take a total or take some other way. There are multiple ways of actually measuring that. Okay, let's get on to the good stuff. How do we know if our model is good? So we've created a model, right? And it's the y value is equal to the slope times x plus the intercept. Okay, and we run it. How do we know if it's any good? Well, there are two values that we look at. Actually three, but I'm going to talk about two first. The first one we're going to look at is r squared, and the second one we're going to look at is the F statistic. R squared is the amount of variation that our model is able to account for. And there's statistical processes that regression goes through to determine that for us. So it says, okay, I'm going to build this model for you, and I'm going to look at my predicted y values for all of the records, and I'm going to look at my actual y value for all of the records, and I'm going to determine how close they are for the entire data set. And out of that, I'm going to generate an R squared value, and that R squared value is something that we use to determine the quality of the model. It is always a value that is between 0 and 1, so it'll be point something. We usually want R squared to be above 0.0 or 0.7. And when we get to 0.7, 0.8, we're accounting for 70 or 80% of the variation in the data set. And that's good, and we want that. That's a good model because we're most likely going to be accurate when we make predictions based on that. That means that our independent variable x was a good predictor of our output variable y, and we have a reliable model for future data, and that our slope and intercept are useful. So we want an R squared about 0.7 or higher, and that gives us an idea that our model is pretty good. What is the F statistic? The F statistic is really a ratio. It's a ratio of the amount of variability that we can account for under two conditions. The first condition is if we just calculate the mean of all of our output values, our dependent variables, we just calculate the mean in our training model for all those, we've got a situation where we have no model. We're just looking at the mean. And so we would go through and look at then all of the data points and calculate the distance from a mean line. And that would be something that would probably give us quite a lot of error because the data points would be far from the line. And I've got a visual that actually shows this. But when we have a regression line, now we have a model, okay? And so with the model, we have a vertical line or a diagonal line, and the diagonal line is hopefully, as it is designed to do, much closer to the data points. So we're going to generate a lot less error. So the total error is the distance from the regression line to each data point for all data points. In our earlier model, the total error is the distance from the horizontal line or the mean line to each data point for all data points. So what we're really doing is we're comparing how much error did we get with no model to how much error did we get when we had a model. And we want that to be a fairly high ratio. We want it to be high because we want this model to account for far more error, account and explain away far more error than when we have no model at all. So the F statistic is typically something that is greater than 1. It's measured on a scale, it's a continuous numeric scale. It's not limited to 0 to 1. So it's something that we usually want greater than 1. We don't want it far greater than 1. If it's 1, it means that there's as much error in our model as there is when there's no model. That's not very good. So we want it to be 10 or 15 or 20 or some higher number that says, you know, we were able to account for a lot more error with the model than we were without a model. And that's as simple as I can explain the F statistic. Here's an example. It's not a great example because I'm not that great of an artist, but this is our horizontal line, and presume that this is our mean. This is our mean value for this data set. The mean value would be about 212. So 212, if you average the value for all these, is the mean. You can see that in many cases, the data points are really far away from this line. In a couple of cases, they're kind of close, but a lot of them are going to be really far away from that line, further enough away that they're going to generate quite a lot of error. Okay, so it has some amount of error there. And it's a pretty high number. Then we come through with a regression line, and the regression line, remember, is designed to be as close as possible to all data points. And what we've done there is we've explained away a big chunk of the error that was generated with the mean line. We can now account for it with the regression line. And so this is going to explain away a lot of that error, and it's going to wind up giving us a pretty high F value because this is so much closer to the actual data points then it generates a lot less error. And so the ratio is going to yield an F statistic that's going to be fairly high. We also talk about significance. Significance, if you're familiar with statistics, you're familiar with p-values, it's the same thing. But basically, many data mining tools use common statistical tools. Regression is one of them. And common statistical tools often have measures of significance or p-values. P-value, in short, is just basically what is the chance that I could get the results I got purely by chance. So a high p-value is a bad thing because it means that you could have gotten the results you got purely by chance. There's no real confidence that your test or your model really did a good job. The lower the significance, though, the lower the likelihood that my results are purely by chance. So for just a couple of examples, if I flip a coin, I have a 1 in 2 chance of getting heads. That's really not significant because I have as much a choice of getting one as I have of getting the other. So there's real no significance there. The same things if I roll a die, I have a 1 in 6 chance of getting a 6, but that's still, it's pretty chancy. Who knows? So it's not significant. But in my example, if my x variable does a good job of predicting my y variable, and I get a high f value, which means I've accounted for a lot of the variation, what is the chance that it was purely by chance? Probably not very high. In fact, it's probably pretty low. So it's going to give me a significance value that is going to be fairly low, and that just basically means that there's a really low chance that you got the results you got purely by chance. So that's what we use significance for. So to recap, 5 things we want out of regression. We want the slope. That's the rate of increase or decrease in y when x changes by 1 unit. But it also determines the steepness of the diagonal line, of our diagonal regression line. The intercept is the starting point, or the place where the regression line crosses the vertical axis. The r-squared value should be greater than 0.7, and it is telling us how accurate our model is or how much of the variation our model is able to account for. The f value should be greater than 1, hopefully much more greater than 1, and it tells us how much better our model was than when we had no model. And the significance, otherwise known as p-value, should be low, usually less than 0.05, and that usually applies to the f value. The f value is calculated based on how much better our model is than no model. And the p-value is telling us what's the likelihood that we got the f value we got purely by chance, and we want that to be fairly low. All right, this is kind of hard to see. Should have checked this out a little better. Anyway, this is a summary output. We have regression statistics, and you'll get to see this live when we actually cut over to Excel. One of the things you'll see right at the top is your R-square. And this is an example I'm going to run through. Your example is going to be different, so you will not get these numbers. So when you run through your example in Excel, don't think you're going to get these numbers. Okay. My R-square is 0.444. That's not great. It's not 0.7, not 0.8, it's 0.444. So that tells me that I probably don't have that great of a relationship between my input variable and my output variable, meaning that my input variable is probably not going to be a great predictor for my output variable. I'm going to get a lot of error. Okay. If I come over here, I see that, well, at least I have an F statistic of 31, so my model did a much better job than no model at predicting the variability. And I have a significance that is really low. This is a p-value that is good. So the f value is very trustworthy. It's just that the r-squared isn't great. Down here, I've got my intercept. This is, again, where we cross the vertical axis. We cross it at 30.485. And my sales, it gives me my sales, but that's really my slope. It's just the name of the field. And the slope is 0.1917. That means that for every increase in my sales for the year from January 1st to November 30th, I'm going to see a 19-cent increase in my projected sales for Christmas time. Okay. Here's visually. Again, slope 0.19. For every increase in year-long sales, annual sales, I get a 19-cent increase in my Christmas sales. These are Christmas sales over here on the vertical axis and annual sales on the horizontal axis. My intercept is 30.49. That's the place where I'm going to cross. If I extend the linear, the regression line, I'm going to cross at 30.49. That's my starting point. Okay. My r-squared is 0.444, which tells me, look how scattered this is. It's probably not a surprise that it's not a great model, and also there's not that many data points. So not terribly surprised that the r-squared isn't very high. My F statistic, this would be my mean line. That's a mean of 114. So the mean for all these data points is 114. And with this line being plotted, that's when there's no model. There's no model at all. I'm just saying average sales were 114. So I'm going to guess that average sales for every customer at Christmas time is going to be 114. It's really far from my data points, and it's going to generate a whole lot of error. And so that's not great, okay? But my regression line is a lot closer to my data points. Even some of these out here, it's still a lot closer. So it's going to generate a lot less error. And because of that, I'm going to come up with an F statistic that's going to be 31.94 because my regression line is closer than my mean line to all of my data points. And my significance, as we've already seen, is very low, but significance is relevant only to the F value. It determines how much we can believe our F value, and we can believe our F value very much. So what do we do with this information? Well, once we were able to determine the slope and the intercept, we build our model. And in our case, X is going to be our annual sales, the sales from January 1st through November 30th, and Y is going to be our sales at Christmas time. And we will use the amount that the customer bought from January 1st to November 30th to predict how much they will buy in December. Okay, our general linear model is, remember, this is just a reminder, our output or predicted value of Y is equal to the slope, which remember we saw was 0.19 in our example, times the X value. And we multiply that out and add it to the intercept, which was 30 point something, I can't remember the exact number. And then if we had it, we would add the error or the residual, and that would actually give us our actual Y. Our actual Y, because we're taking now into account the difference between the predicted and actual. Our model is going to be our predicted Y equals, well, there are our numbers right there. Our slope is 0.1917 blah, 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 times X plus 30.485 blah, 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 blah. That's going to give us a predicted value for Y. Let's look at a couple of examples. If X is $100, our predicted Y is going to be our slope times the input value, which is $100, plus the intercept, and you calculate all that out, and you're going to get 49.66. So $49.66 is the amount that the customer is predicted to spend at Christmas time if they spent $100 between January 1st and November 30th. What if they spent $250 between January 1st and November 30th? Same thing. Our predicted value is Y. It's going to be equal to our slope times our input value of X, and we are going to add the intercept, and we are going to come up with a value of $78.42, and we predict that the customer will spend $78.42 at Christmas time if they've spent $250 for the rest of the year. Again, these are predicted values. They may differ from the actual values. What we want is we want them to differ as little as possible from the actual values. The difference is error, and we want the error to be as small as possible. All right. Now that we have our model, we can use it to make predictions for what we don't know. So we've got it based on our training data. And on our training data, we had the sales for the year and the sales for Christmas. Imagine now we're a year or two in the future, and we don't have the Christmas sales. We don't know what the Christmas sales is going to be. Or we're getting actually, what is it, October-ish time frame. We're getting close, and we want to start to know what have they spent so far, or what did they spend last year, so we can start marketing products and sales to them. So this is how we would use this model. We would take the inputs. We only have the inputs. We only have the X values, but we don't have the Y values. We would create predicted Y values. And if our model is accurate enough, we can believe those Y values, and that's going to be what we can use to actually determine how we handle our customers. So maybe somebody gets marketed to, somebody, we don't send anything to them because they never spent anything during the year, so they're probably not going to spend anything at Christmas time. Or you might even decide to put together like a gold customer category and put customers in there because we know that in December, they're, with a little push, they're likely to spend a lot more. All right, now we're going to see how we're going to do this in Microsoft Excel. And this is actually, pay attention to this because this is what I want you to do in your assignment. You'll find the right, there it is, file. Okay, I have customer name. This is sales from January 1st to November 30th. This is Christmas sales. This is my training data, so I have both values. And the state of residence, Washington, irrelevant for our purposes. How many records do I have? I have 42 records. Okay, that's not a very big data set. Ideally, what we'd like to have is something like 4,200 or 42,000 records to build a model, but this is good enough for our purposes. So what we're going to do is we're going to build a model that predicts the output, or Christmas sales, based on the input. Now, to get to this, you have to go to the plugin for the analysis plugin. You should have loaded the analysis plugin. But if you hit data and go over right by where you've been starting solver and hit data analysis, you're going to get a list of all of the different statistical models and statistical things you can use in Microsoft Excel using that plugin. And the one we want is regression. So click on regression and click on OK. Now we have to tell it a couple of things. First of all, I'll take these out so we can type them in. All right, what is our Y range? Remember, these are our predicted values. These are the things, these are the outcomes. And so the thing we're trying to predict here is the Christmas value. So that's going to be C1 to C43 was the last row. And then what is our input range? So what is our independent variable or predictor range? That's going to be B1 to B43. Okay. So we are going to use B1 through B43 to predict C1 through C43. We have to click the box for labels because we have labels. And so we will ignore the first row. And we're going to let it just go into a new worksheet. That's fine. And we're going to ask for residuals and it's standard residuals. Residuals, remember, is our error. It's our predicted, the difference between our predicted and our actual values. And our standardized residuals is just a converted way of looking at it. And it's looking at it on a scale of 1, I believe, -3 to +3. It's an easier way to be able to see how much error there really is. Okay, if we click OK, boom. All right, it's going to give us all these values. Let's make this look a little easier. I'll highlight that, click on 1, and it will space them all out correctly. We have some summary output values. We have multiple R, which is what's used actually to derive R square. So R square here is 0.444, and we already knew that because we've seen that in our data set. Adjusted R square is slightly adjusted down. I'm not going to go through each one of these. I'm just going to go through the ones I want you to remember. So R square is there. Then we come down and we look at our F statistic, 31.94, and our significance on the F statistic is really low. So this is a good, believable F statistic. We're able to calculate it. And what this really means is that our model accounts for a lot more variability than having no model. That's good. It's just too bad that we have this in R square of 0.444. Then we come down here and we see we have our intercept, which is 30.485, and we have our slope for sales, which is 0.1917, and so on. The rest of this I'm not going to talk too much about, except down here we will see that for observation number 1, the prediction that was made was 100.079. It has a residual of 0.933 to the negative, which means that the actual value is $9.33 lower. This is a standardized residual, which is a measure of these distances in relative standard deviation. If we go back to our data set, remember this just created a new sheet for us. If we go back to our data set, our first Christmas sales, the actual Christmas sales was $90.74. So it's predicted sales of 100.7079. So it's a little off. And each one of these is going to be a little off. Each one of these is going to be, in some cases, we're really close. We're $3.17 under. In some cases, we're pretty far off. We're $49 off. Okay? But nothing's huge, nothing jumps out. And we're getting a better idea of what these customers are likely to spend at Christmas time. These are all of our 42 projections, all of our 42 predictions. And so now we can take these values, assuming that we didn't already know them, in a later data set, and we can sort them. And we can say, oh, this customer is going to spend a lot of money. Let's send him a whole lot of marketing materials. And this customer is also going to spend a lot of money. We'll send him a whole lot of marketing materials. Here's another one. Here's a really good one. Then on the other side, we have some that maybe aren't going to spend quite so much. This one's only going to spend 52. We may not worry too much about him. Somebody 63, but sort of you get the picture. And that's really what we are trying to do with linear regression is to make these predictions and make them as accurate as possible. Okay. Part of the reason why we have a R squared of 0.444 is that the residuals and the predicted values are the predicted values are kind of far from the actual values, and the residuals are kind of high. And that's probably what accounts for the fact that we got such a kind of low R squared. All right, back to the PowerPoint. All right, now we've seen how we do this in Microsoft Excel. You can watch that part of the video again if you want, and you can see exactly how to do it. Your assignment. I have given you a file. It is different than the file we just looked at. It will be loaded into the module, or should have been loaded into the module by now. It looks the same, but it's not. What I want you to do is I want you to run regression on it. Your X value is going to be your sales column, and your Y value is going to be your Christmas column. I want you to determine slope, intercept, R squared, F, and significance for this data set. Once you do that, when you run regression, you'll get all those values, and you'll have that on a separate sheet. Save that and turn that in as this week's assignment. If you have any questions or concerns, be sure to let me know. Thanks.